Hey, good afternoon, everybody, and thanks for tuning in and welcome to our third season of the How Do You Know program. So excited to be back on the air, and we're going to have a variety of programs. We're undoubtedly going to hit program number 100 this season. So if you have special requests, and that goes for throughout the season, if you're seeing something in astronomy news and you say, I wish Doc were here, I could ask him about that, then please email your questions, and you can email them to me directly at astronomyforeducators@gmail.com, or you can email us at Explore Scientific. So just a quick public service announcement for everybody. I'm sure everybody who watches this program knows what these are. These are eclipse glasses. Yeah, friends, I got to tell you, I was talking to my good pal Scott Roberts about eclipse glasses just last week, and he said during the 2017 eclipse, as it got very close, the people just at Explore Scientific, our sponsors, they were getting as many as 35,000 orders a day for eclipse glasses. Gee, guess what happened to lots and lots and lots of those people who waited until the very last minute to order their eclipse glasses? It's not a happy story. They were disappointed. We've got an annular eclipse coming in October, and then next April in 2024, we have a spectacular total eclipse, which is slicing across the Midwest again. Friends, if you want to go out and observing, you want to get yourself a pair of eclipse glasses, get them on order now. Explore Scientific has them. No matter what retailer you go to, these are certified safe. Last time the catastrophe was that, guess what? The sharp folks saw that there was demand for eclipse glasses, and they started making fake ones. What do I mean by fake? The solar film inside wasn't good enough to block all the harmful ultraviolet and other radiation from their eyes. Folks, please, if you're going to be observing the solar eclipses, do it safely. Get yourself a pair of eclipse glasses from a reliable astronomy retailer. Lots of folks are going to have them. Explore Scientific is supplying lots and lots of retailers across the country. So if you see them there, if it says Explore, you know it's a high quality piece of equipment. These are very affordable, lots of fun. And if you order them now, put them away somewhere safe so you can find them on eclipse day. I've heard that story too. I know I ordered them, now I can't find them. Well, anyway, we'll be doing some programs on the eclipse, how to observe it safely, and fun techniques and projects. We'll be doing all of that stuff. Keep an eye out for the Skies Up magazine, which is an online journal, and they're going to have articles there too to help you enjoy the eclipse. Now, going on into program number 78, Dark Matter or MOND. Well,
Dr. Barth.
Yes, sir.
Don't forget your book.
I will not. If you are, friends, if you're a beginning astronomer, or if you know someone who has finally gotten that telescope they've always wanted, or maybe you know someone who's got a telescope already, but they're interested in improving their skills, we recommend Star Mentor. That's my latest book, more than 50 activities that are arranged from the most basic to more advanced. They're sorted by season, by type of object. Learn how to control your telescope, read a star map, track objects in the sky. Everything you need to improve your skill set. And when somebody gets a telescope, they inevitably, after a week or two, get the, gee, what do I do now sort of question. The answer to all of those, what do I do next questions, comes in the book Star Mentor. It's not designed as a big read cover to cover, so you don't need to be worried. It's more like a smorgasbord. You can dip in and thumb through the table of contents and pick whatever looks interesting for you that night. I hope you'll pick up a copy, and if you do, be sure to leave us a review. There we go. Now, let's go ahead and move on to Dark Matter and MOND. Well, what are these things? And if you ask the average person who's interested in astronomy, they might say, oh, I know what dark matter is. It's this mysterious stuff, and it makes up a very large portion of the universe. And we haven't found it yet. But the thing that's not likely to come up when you ask somebody, even an astronomy fascinated person, what's dark matter? What's not likely to come up? Oh, that's a theory that some scientists have to explain some phenomena, but they don't have any proof that it's true yet. When I say that to people, I know how Galileo felt. It's kind of like a minor heresy. And sometimes I'll get the so not scientific question. Do you mean, Dr. Barth, you don't believe in dark matter? Because it's science, y'all, my belief, yours, or anyone else's makes no difference. Makes no difference at all. So what about MOND? What is MOND? MOND stands for Modified Newtonian Dynamics. And basically, these two theories have something in common that's hidden and not often discussed. And what they have in common is Isaac Newton and his theory of universal gravitation. The MOND folks don't think Newton was completely right. Let me, if I was wearing pearls, I would be clutching them right now. To say Isaac Newton is wrong, well, that either makes you a serious, once-in-a-lifetime sort of a genius, or it makes you a kook. People who say, yes, the world's smartest people in history, like Einstein and Newton and Galileo and Copernicus, if you go along and saying they're wrong, you've got to back that up with some pretty serious data. And the fact is, when we look at this and we say we've got these two theories, we don't know which one is correct, or even if either of them is correct. So what's all this about needing to change our theory of gravity anyway? Why do we? Isn't Newton pretty much the man? Didn't the astronauts on Apollo 8, when they were on their way to the moon, and the news, I think it was Walter Cronkite, he said, well, you're up there, you're in between the Earth and the moon. Who's driving the ship? And one of the astronauts quipped and said, Isaac Newton's driving. And he was perfectly correct, because essentially the folks at NASA and everybody, doesn't matter what country or organization they're from, if they're launching a satellite or a spacecraft, if they're trying to fly to the moon or fly to a rendezvous with an asteroid or go to Mars, no matter what they're doing, they are absolutely positively sticking to Newtonian gravitational theory, Newtonian dynamics, and what we refer to as the Keplerian laws of planetary motion. Everything in our solar system moves according to the laws set down by Isaac Newton and Johann Kepler. As you probably know, Kepler was a scientist who in the 1600s, using data primarily from other observers, went and mathematically worked out the laws of planetary motion. The idea that all planets orbit in ellipses, that the farther a planet is away from the sun, the more slowly it moves. This is why Earth at 1 AU takes 1 year to go around, while Jupiter at just 5 AUs takes 12 years to go around the sun once. As you move farther away, planets move more slowly and thus orbits take more time. And when we're launching a satellite or a spacecraft to Mars, we must absolutely pay attention to the laws of Isaac Newton and the planetary motion laws set up by Johann Kepler, because if we don't, our spacecraft will not arrive on time and on target the way we need it to. It will be drifting off course, and if we ignore Newton and Kepler, our space mission is not going to end well, and our craft will be lost. Okay. But along comes one of my favorite astronomers, Vera Rubin, who was an astronomer, who was a mom. She was raising a family, and she wanted work she could work on sometimes from home, and it didn't require a lot. And she says, and she wanted to work that, well, there wasn't a lot of competition. I want to work on something where there's not a lot of people fighting over space and funding. And so she said, I'll take a look at the rotation of galaxies. And Hubble did it with these spectroscopic studies of galaxies to prove how far away galaxies were. Vera Rubin said, I'm going to zero in on a portion of the galaxy, and I'm going to use both spectroscopy and the Doppler effect to measure the rotation of galaxies. Because, of course, if Newton and Kepler are right, then the farther out you are from the center of the galaxy, the more slowly you should orbit and the longer it should take you to go around. And gee, Vera Rubin with her partner, a fellow by the name of Ford. Ford was an instrumentalist. He developed basically the first digital camera. It was a 1 pixel sensor. But by using it in conjunction with a large telescope, they were able, very painstakingly, 1 pixel at a time, to basically use a diffraction grating and this 1 pixel sensor. And they were able to take spectra of objects rotating on opposite sides of a galaxy. So one side should be rotating toward us, the other side away from us. And we can use Doppler effect and we can figure out how fast things are moving. And Vera Rubin made the same assumption that basically everybody else has made for the last 350 years. Isaac Newton nailed it. When it comes to gravitation and the theory of gravity, pretty much everybody assumes Isaac Newton was exactly right. Completely perfect. Matter of fact, the number of people who've basically started out successful research projects with, I think Isaac Newton wasn't completely right and his work needs to be tuned up and adjusted. The people who've done that successfully, very, very small number. Einstein is basically at the top of a very, very, very short list. And it's basically Einstein, followed by Einstein, Einstein, and Einstein. Vera Rubin did not even attempt to modify Newtonian dynamics. She simply said, I have this experimental result which doesn't fit with Newtonian theory, and it needs an explanation. And she called on the greater astronomy and physics community, come explain my data. I have new stuff, and she spent her career working with progressively better instruments, larger telescopes, And basically, she confirmed that when you're talking about something as big as a galaxy, things don't slow down as you get farther away. Instead of having what they call a rotation curve, which shows that the farther away you go, the slower things get, with galaxies, that curve was flat. Nothing slowed down as you moved farther and farther away. It just didn't slow down. It kept going at the same speed, which seems completely nuts. So with this going on, and with Kepler's laws obviously not applying, and if Kepler's laws don't apply, Kepler's laws are a special case of Newton's laws, and so what's going on? Well, the astronomers found themselves in the same place as ancient astronomers did a couple of millennia ago. They had this lovely Earth-centered theory developed by Aristotle, and as observational methods got better over the centuries, they had to keep adjusting the theory, eventually adding in epicycles and all sorts of other things. And what they were doing is something called preserving the appearances. They were tuning their theory to match the data. Something we know now is probably the number one no-no in scientific thinking. We do not mess with data to fit a theory. We have to go ahead and go back to theory, and we have to find a way to either change or throw out the theory and bring it into a new place where it can explain the observations as they are. Well, we have this lovely situation, and no one could explain it. Someone finally came up with this idea, and they said, I know. What we see isn't all there is. Now, this makes perfect sense if you think about our own solar system. Think about what you could see from a couple of light years away. That far away, our planets would be essentially invisible. It's not that you couldn't detect them, because our planets tug on the sun and make it wiggle and move, and you can go back and you can calculate. If our sun is jiggling this way, how many planets, how far away, how massive are they? And the folks at NASA and elsewhere in the astrophysics community have got this down, forgive me, to a science. And they can do these analyses quite well. But in terms of actually seeing these other planets, it's only been done a couple of times with very large planets who are quite close to us. And essentially, virtually all of these planets are too far away, too dim, too poorly illuminated for us to spot them. So we can't see everything. Everything doesn't glow with its own light. But the exoplanet community says if you watch what happens with gravity, you can figure out what's going on. Because things interact gravitationally even if we can't see them. Now, this idea has an old history too. The first new planet, of course, the classical planets being the 5 you can see with your naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Of course, Earth is a planet too, but we're talking planets you see in the sky. So there's those 5 classical planets. The first one beyond that was discovered by William Herschel, 1781. And he named it George. Nobody liked the name George. And Herschel said, but it's my boss. It's the guy who pays me, King George III. So the astronomical community said, no, stick with Greek names. So we got stuck with Uranus, or Uranus, if you like the more Greek pronunciation. Well, once people had found this planet, wow, let's, of course, immediate science fair project, let's make sure it matches Kepler's laws. So they started observing the orbit of Uranus. The only difficulty, of course, it orbits in something crazy like 165 years, so it took decades to get enough data. 20 or 30 years in, they're finding errors. And people are saying it must be another planet out there. And 3 people were involved in the discovery of the next planet. John Couch Adams, who who was the astronomer royal for England, he did the math and predicted here's a certain spot in the sky. And he wanted to publish, but he wasn't astronomer royal then, and his boss didn't want to put the word out. So he basically sat on his discovery and shared it around with some friends. A French astronomer, Urbain Le Verrier, and he has a whole string of names, but we'll stick with the easy ones. Le Verrier also does some calculations, and he is perhaps the best visual astronomer since Tycho Brahe. He's an amazingly precise, and like Brahe, he's kind of an antagonistic man who kind of gets under everybody's nerves, and he's not well liked, but he's very, very good at what he does. And he says, aha, I found a place in the sky where the new planet should be. And his place is pretty much right on top of where John Couch Adams said it would be. The odd thing, neither man goes, takes a telescope and looks. It was some months later, and a German student, a 19-year-old astronomy student, writes to Le Verrier, Monsieur, I have followed your work with great interest. I have noticed you've published this claim that there is a planet to be found in this location. May I have your permission to take a telescope and look for this planet you claim is there? Such were the niceties of 19th century science. Le Verrier, of course, gives his blessing, and it is Johann Galle in 1846, and he goes ahead and finds the planet Neptune, which indeed was predicted by Le Verrier and by Adams. So you've got an Englishman, a German, and a Frenchman go looking for a planet. It sounds like a joke, but believe me, you can still start fistfights with astronomers from those respective countries by saying, and who discovered the planet Neptune? In any case, we can have a whole discussion about that, and we have. The thing is, when Le Verrier found observing the planet Mercury, it doesn't match up with Newton's predictions. It's not exactly right on the money. How far is it off? Mercury drifts, says Le Verrier, something on the orbit of 0.001 degrees per century. Think about that. 0.001 degrees per century. Think of the kind of absolute precision with, for the Americans in the audience, Civil War era, 1840s era instrumentation. And Le Verrier does these measurements, and because he is Urbain Le Verrier, and everybody knows what a complete, awesome master he is of high precision measurements and instrumentation, everybody basically says, yeah, the French guy must be right. Mercury is drifting off course. Le Verrier made the same assumption that the dark matter people make. Newton is right. Newton is not just right or pretty much right. Newton is absolutely right. Newton is so right that this error of 0.001 degrees per century could not be a problem with Newton's math or Newton's theory. Newton's math and Newton's theory are perfect, you see, according to people of the day. And so Le Verrier says, well, I was right about Neptune, wasn't I? There's another planet. And he does the calculations, and he finds that a small planet that was about the size of Ceres, the asteroid, in other words, considerably smaller than the moon, that this object orbiting very close to the sun, so close to the sun that no naked eye observer in many millennia has ever spotted it. This thing is there, and it's tugging just a little bit on Mercury, and it's causing this tiny deviation. Newton is right, and something else is lurking in the dark that we can't see. The next 75 years, because Newton is considered to be the man, the myth, the legend, almost a god of astrophysics. And Leverrier is kind of right up there rubbing elbows in terms of somebody who's awesome at astrophysics and observational astronomer. Well, Leverrier must be right. The planet must be there. And they found other planets this way. So the search is on. And people are trying solar scopes with disks to block the sun. They're observing during total eclipses. And over the next 75 years, there's lots of people who say, Eureka, I've found it. I've seen the planet. Oh, and what did they call it? Vulcan. The planet Vulcan. I've seen Vulcan. The only problem is nobody can confirm anybody else's work. And if you see an object and you claim, aha, it must be there and it was this close to the sun, it's fairly easy to establish an orbit so that other people can look for it. But nobody's observation gets proved out with other astronomers saying, yes, I found it too, just where you looked for it. Compare that to Neptune, when anybody could look up with a modest telescope and go, yep, it's right there. Where Adams and Leverrier said it was, and where Gale found it, it's right there and I can see it. But Vulcan, no, it was very hard to find. So it turned out the planet Vulcan, folks, didn't exist. It didn't exist. What did happen is that in 1915, this German guy comes out with this theory that says basically Newton was a little bit wrong, and under these extreme conditions you need to calculate stuff this way instead of his way because he gets it wrong. 1915. World War I is raging. The Kaiser, Germany, is the aggressor, and millions of people are dying. Both across all of Europe, people are dying by the millions. When Germany loses the war in 1918, guess what? Germans, in general, are not very popular. And German scientists are not very popular with European scientists. But there's one European scientist, a British astronomer named Arthur Eddington, and he says, you know, I don't care about his nationality or what his country did. His math looks really good. I think we should check his theory. I think we should go look. What does Einstein say? That's the German guy. He says, oh, gravity bends space and light follows the path. And Einstein says, it's not really space, it's space-time. And he has this whole crazy theory. And moreover, he says, you know what? My theory with the bendy space, it accounts exactly for the problem with Mercury's orbit. How can you prove it? If you go look during an eclipse, the gravity from the sun will bend light. And the stars you're looking at near the sun won't be here, they'll be there. They'll be out of position, and Einstein predicts exactly the small deviation that we should be able to see with a camera. And Eddington finds the funding, builds the equipment, and he sends 2 expeditions, one to West Africa, one to South America, where the weather is expected to be good. The South American edition is a bust, but the eclipse expedition on the island of Principe off the west coast of Africa is a winner, and Eddington gets the photographs. He proves Einstein was correct, and he makes him an instant celebrity. Funny, because the guy whose theory was proved got to be a much bigger household name than the man who actually did the experiment and proved it. Everybody has heard of Einstein. Eddington, sadly, not so much. But in any case, we get this situation where they say, oh, well, we predicted this thing because Newton was right, and it turned out he wasn't. It's happened before. The luminiferous ether. If light's a wave, it must have something to wave in. Guess what? Michelson and Morley did an experiment and proved that the ether was not there. It didn't exist. The old theory needed to be modified, and hence we got electromagnetism. We've done it many, many, many times where everybody is convinced that we have the right theory. But in fact, the theory that we all assumed was perfect was not. It needed modifications. These discrepancies, whether it's, oh, look, Mercury's not in its quite correct orbit. Oh, look, Uranus, this new planet we discovered just 30 years ago, it's not moving the way we predict it should. Oh, look, says Vera Rubin, galaxies don't rotate the way we thought they should. These discrepancies are the cracks. And we go up and we look through these little cracks, these keyholes in the edifice of science, and we, like Howard Carter breaking into King Tut's tomb, we look inside and we say, it's full of things, wonderful, wonderful things. And what's dark matter do? The dark matter crowd says, no, 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 no. Newton is perfectly correct. Newton is perfectly correct, and in order for galaxies to rotate this way, all we need is a hugely massive shell. Basically, a galaxy is like one of these beautiful glass paperweights with the glass flower inside. And you know, wow, how did they make that? Well, if you think of what we see for a galaxy, out beyond the outermost edge of the galaxy is a huge, massive, dense layer of material. I shouldn't say dense, very, very massive. That would be more accurate. This massive, outweighing the galaxy itself, and according to some calculations, so this massive amount of material, and it surrounds the galaxy, and lo and behold, if you indeed did have a galaxy surrounded by that much matter, then in fact, it would change the rotation curve because there would be things farther out than the galaxy core, and they would be pulling on the stars, and they would be changing the rotation curve. And when you tweak the math like that and say, oh, let's throw in a couple of galactic masses of particles that exist in a shell around the galaxy. Okay. Well, gee, that works, except no one has ever, to this day, found dark matter. We keep doing experiments, and what the experiments keep finding is that, in fact, gee, when we look at this, we don't find it. The only way we know dark matter exists, and I put this whole phrase in quotes because you hear this a lot in popular scientific discourse. The way we know dark matter exists is that dark matter explains this problem. It's like, oh, I hear a bump in the night. It must be a monster. How do I know it's a monster? Because I heard a bump in the night. Yes, if that impresses you as somewhat circular reasoning, the dark matter crowd has that all down pat. We know dark matter exists because we see the gravitational effect of dark matter. And if the gravitational effect is there, and of course Newton is perfectly right, then dark matter must exist. That's so many fallacies in one paragraph, I'd have trouble unpacking it for you all. No, sorry. Saying that dark matter preserves the appearances, therefore it must exist, this is like saying epicycles preserve the appearances of the Earth-centered solar system. So the Earth must be in the center, and the epicycles must be true. No, because something appears in our theory doesn't make it true. It makes it an idea worth exploring, but only data, evidence, and every time we've looked for, we had a lot of good ideas about what they were. Some people said, oh, they could be machos. You know how the astronomy and physics community likes little anagrams, right? Machos, massive, compact halo objects. Gee, they said, we could have billions upon billions of Jupiter-sized objects. Too dark to glow, you can't see them, but massive enough to do all this. Then they said, oh, well, we didn't see machos. Matter of fact, we know big objects like Jupiter, they emit radio waves. We see no evidence like that of these objects. So we're pretty much sure machos, no, they're not it. Then they had another particle. They said, oh, WIMPs, which stood for weakly interacting massive particle. So it has to weigh a lot, but it doesn't interact with anything except by gravity. And how does that work? We don't know. Oh, by the way, the WIMPs have been knocked out because every experiment we do proves that they set a boundary. It's like saying, oh, I'm looking for a creature in the dark in the woods. How big of a creature are you looking for? Oh, well, it has to be at least 6 foot tall to be a creature. You know what? You're going to go through the woods and you might look at a lot of things before you found something that big. On the other hand, if you keep setting the limit smaller, it's a creature if it's bigger than, well, what would you find in a forest? A squirrel, a rabbit, oh, a mole, oh, an insect, a cricket, an ant. So the dark matter people have basically gone through the forest with a finer and finer screen. And these experiments have been limiting the size, no longer a massive particle. The latest research, is just out this week, indicates that the most massive a dark matter particle could be is about 1/5 the mass of the proton and potentially much smaller. Well, we look at that, and that work, if you're interested, friends, oh, I have a note on it here because I got this just late. Fellow named Jardin, Daniel Jardin from Northwestern University, and he is part of the Supercryogenic Dark Matter Search, or Super CDMS. And Mr. Jardin, who's observing this, he's a doctoral postdoc fellow, I believe, he's going ahead and saying, nope, can't be bigger than 1/5 of a proton, potentially significantly smaller than that. Do we know things that are smaller than that? Oh yes, electrons, neutrinos, we know of lots of things that are smaller than that. The trouble is, the things we know about, they don't show up in the cold dark matter hunt. They're never turned up. And to date, there is zero evidence of the actual existence of dark matter. We have a theory that works well with our observations, and we have observations that have been done to test dark matter. But in fact, those ideas have never borne scientific fruit of saying, aha, eureka, here it is, we've detected a particle. Now, the idea that we need to search for a long time before we find a particle doesn't necessarily mean it's not there. The Higgs boson, discovered in 2012, and we looked for that for 50 or 60 years. The same thing with the neutrino. That was predicted theoretically. Well, how are we going to find it? There's no electric charge. We eventually found that. The neutron, all of these various particles were predicted before they were discovered. And predicting the particles, I see Beatrice has joined us. Hello. And Scott's not with us this afternoon, Beatrice, but I will pass on your greeting, and it's nice of you to remember him. And so we looked at this, and there's Mike. What is the matter? What's the matter with everybody? It's dark in here. That's because you're in your observatory, Mike. And then there's Norm, who says he has dark matter between his ears. Yes, dark matter jokes. Yeah, I think we're going to pass on dark matter jokes. There's so many and so little time. The interesting things, when you keep on hunting for something and you don't find it, when do you say, I must stop now because it's not actually there? And the unfortunate answer to that question is, there's no real stopping point. And you might go, come on, after you looked here and there, it's kind of like you're looking for something, you're looking for your wallet or your car keys or something, how many places do you look before you give up and say, well, it's lost. I can't find it. It's not here. It's not there. It's not anywhere. Apologies to Dr. Seuss. But if you keep looking and you keep not finding, eventually you may decide if it's whatever it is. Oh, gosh, I guess I've lost that. I'm going to stop looking now. The scientists are more stubborn than that. And sometimes the search has gone on for centuries. But keep in mind, we don't prove something isn't there by not finding it. And that seems like, wow, that for a lot of people who are not experts in science, that one is a head cracker. What do you mean if we don't find it, it doesn't exist? Well, of course it doesn't exist. If it existed, we'd find it, right? That assumes that we're really clever and we've got really good materials and unlimited money and time to look. But no, it doesn't prove this sort of thing at all. What does or what would prove that dark matter doesn't exist? Well, you'd have to have another theory that explains the phenomena that dark matter tries to explain, but it also goes on to prove experimentally that dark matter cannot exist. Your theory answers lots of other questions, and according to your theory, dark matter cannot exist. And you might say, but gosh, how do you do that? Galileo did it. You realize he didn't prove the sun was in the center of everything by saying, oh gosh, I've discovered moons around Jupiter. Everything doesn't orbit the sun, or rather the Earth. That didn't do it. What did it was finding the phases of Venus. And if you play with the phases of Venus, and yes, we have a How Do You Know episode on this, you find out that, gee, the phases of Venus cannot happen with the Earth in the center. It's not possible. The Earth cannot be in the center of the solar system, and you still see phases of Venus. And that proved that the geocentric system was false. The same way Einstein's experiment proved that Vulcan didn't exist because Vulcan wasn't necessary. Einstein's modification of Newton's gravitation, what we call the general theory of relativity, showed that, one, Vulcan isn't necessary. The sun's bending of space-time accounts for Mercury's orbit. And if that's all Einstein did, it would still be two conflicting theories. But what Einstein's theory eventually did, it said this is caused by the bendiness of space-time under the influence of gravity. And because space-time bends, light will also bend. And Einstein predicted that at the very same time. In fact, had he said, my theory predicts bendy light and no planet Vulcan, and the bendy light thing, stars out of position, had turned out not to be true, Einstein's theory would have been thrown away. Nobody would have accepted it. It was only when he proved things and predicted things that were turned out to be true that the other theory said could not happen. Newton's classical theory says light goes in a straight line, period. It doesn't bend. Einstein proved Newton needed to be modified. Not that we throw it away, no baby in bathwater problem for us. Einstein's relativity only comes into play where we have a huge amount of acceleration or a relatively huge amount of gravitation. And apart from those two exceptions, we find Newton's gravitation works perfectly well. Thank you very much. But how about the dark matter business? Is Newton correct and dark matter exists? We haven't found any evidence for that at all. Now it's true, dark matter is by far and away the most popular theory in all of astrophysics when it comes to explaining Vera Rubin's results of non-Keplerian rotation. But it's not the only one. There's another theory called MOND. MOND stands for Modified Newtonian Dynamics, and it was developed, excuse me, by an Israeli astrophysicist named Mordecai Milgram. And Dr. Milgram, I hope I'm saying your name correctly. If not, my apologies, sir. Milgram came up with this idea of MOND, and he said under very large scales of time and distance, Newton's rigid rules for gravitation break down, and they are modified slightly. And because of this modification to Newton, you can explain everything we see with galactic rotation without having to invoke dark matter. And in science, it has been true for more than a millennia. We know it as Occam's razor. Generally, given two explanations, the simplest one is almost always true. We sometimes hear phrases like, if you hear hoofbeats, think horses, not zebras. Unless, of course, you're in southern Africa, and maybe then it's zebras. But the simplest explanation is almost always accepted as true, unless there's very, very good evidence to accept the more complex idea. Well, MOND is indeed a simpler idea. It requires the addition of nothing. It doesn't require you to add anything else to the materials which are already there out in space. Galaxies, stars, dust, gas, nothing changes. Now, interestingly enough, the dark matter idea works pretty much only for very, very big objects. Dark matter works for galaxies. And dark matter, as we know it, things like solar systems, why don't we have a dark matter halo? Well, turns out we don't have enough mass. We don't have enough gravitation to hold dark matter in thrall. And so we're not big enough. You go, okay, well, that makes sense because all sorts of things are determined by size, how long a star lives, what happens when it dies. Do you get a white dwarf? Do you get a neutron star? Do you get a black hole? All of these are dependent upon the initial size of the star, so why not MOND, gravity, being modified in extreme situations with very large, very massive objects? After all, Einstein said gravity needs to be modified where we have very strong gravity fields, very dense, compact objects, or very, very massive objects. And all Milgram is saying is, yeah, that applies in other ways and places too. Now, this week, and I just saw this article, and I'm going to have to go ahead and look this up and provide a link for you. But if you search, there's a recent study just released in the last week or so about the motion of binary star systems. Why binary star systems? Well, you have binary star systems that orbit at immense distances. You have some binary star systems where things are orbiting light years away, where binary systems are just huge, and the masses are quite small, and they are only in orbit around each other because they are in very, very empty places. Because if there were other things around, it would mess up that nice binary. But when we look at these wide binary systems, is what they're called, gee, guess what? According to the most current study, the wide binary pairs do not follow traditional Keplerian orbits either. They follow orbits which are much, much closer. In fact, they orbit as predicted by MOND. The interesting thing there, and this may be a death knell for dark matter, because if this work holds up, in fact, these systems are too small to have anything like a dark matter halo. And in fact, if they had a dark matter halo, we should see other effects which we don't see. So Is this a case where MOND is going to be the come from behind victor in the struggle between two theories? Well, it turns out that we can't say that for sure. We just don't know. And this is part of the great frustration of being fascinated by what some people refer to as the bleeding edge of science. You've heard of the leading edge, then there's the bleeding edge. The stuff that's just coming out. You see this in preprints. It's not even publicized. It's not even published in a scientific journal. And you see these new ideas coming out. Can you go with the crowd and say, well, 99% of astrophysicists can't possibly be wrong, but that in itself is incorrect? We do look back in history and we see that popularity of a theory gives it no weight. Virtually everyone in the time from Copernicus to Galileo and even after Galileo, everybody thought the Earth was fixed, unmoving, unrotating. It was the center of the universe. Everything revolved around us, including the stars themselves. The entire universe revolved around the Earth. It was all tied up with theology and other things, but that doesn't matter. It was a current scientific astronomical theory. It was talked about. It was researched. It was studied. It was in textbooks. It was taught at university level. This was the theory that everyone believed, that everyone knew to be true. Of course the Earth is in the center. It got so bad that, in fact, Galileo was called a heretic for denying the fact that the Earth was in the center of the universe and everything rotated around it. It had gone from, this is the most popular, to everybody believes it, to if you don't believe it, you're not a good person religiously anymore. You're a heretic. We condemn you. We will charge you with a crime of not believing the current theory. We'll put you in jail. We'll take away your livelihood. Well, thank goodness we don't do that stuff anymore. My producer just laughed because he knew I was making a funny joke. Gee, guess who's one of the least popular guys in the astrophysics community today? Mordecai Milgram. Guess what sort of theory you would have an awful time securing funding for? Studying MOND. Why? Because the other theory is so much more popular. It must be true, and people who control funding are not always, should I say never? Maybe. I think I'm getting nods. I should say never. The people who do this are never the current people studying on the current edge. The people who control funding are much farther down in the scientific and economic hierarchy of research. And gee, if you were a person whose job depended on funding things that were popular and got you good results, would you fund research into an unpopular theory? And you might say, but science doesn't really work that way, does it? Well, yes, it does. Science is a human endeavor. So the frustrating thing, friends, we find ourselves like Schrodinger with his famous cat. We have two theories. Which one's live and which one's dead? Frankly, we cannot know. Not that we just don't know, we cannot know until some brilliant person comes up with an experiment that not only demonstrates, oh, my pet theory proves this true and correctly predicts, but also your theory, rival, it's my scientific rival, cannot be true. We've shared this and talked about it many times on this program before. Thomas Kuhn. and the idea that science doesn't progress as a nice help me up the stairs one step at a time. Doesn't progress that way. It's a cage match. Many scientists, probably a majority of them, make their living by challenging other people's results rather than doing new and innovative research. And it is a cage match. It is a last man standing. You may have heard of the room temperature superconductivity. And people came out and said, we've found a room temperature superconductor. You know what happened in the scientific community? There was an immediate rush. And people said, we're confirming your results. But if you talk to the people in the research labs, they said, nah, we're sure they're wrong. We're not trying to confirm their results. We're trying to shoot them down. We're trying to get credit for destroying their idea. And it seems like a fairly negative sort of attitude. But in fact, this is what makes science strong. Fighting, battling, researching, seeking to prove ideas false, which can be absolutely a guaranteed result. If you prove something false, that's forever. Proving something true is an indefinite proposition. We always need more and more confirmatory evidence to get something to know that it's true. And in fact, we can never prove a thing true. We can say all the evidence, 99.99% of evidence. But if we're not arguing based on evidence, we're just talking about what we like and what we dislike. And we might as well be talking about favorite movies or favorite songs or favorite artists. It's an opinion poll. And science isn't about opinion. Well, do we have any last minute questions that have come in? No? Okay. Once again, I've stunned the audience into silence. Either they're all impressed or they're aghast, one of the two. Anyway, we will remind you once again, please go take a look on Amazon and find a copy of Star Mentor. If you own a telescope or a pair of binoculars, or you know somebody who does, an ideal gift for them. So if you're shopping for that astronomer, science nerd in your life, then by all means, if you've got somebody, and you know what, it's coming up to that time, people say, oh, it's summer, Christmas isn't for months. Clever people who want big presents like telescopes are already hinting. So if you have somebody in your life who's already hinting, wow, the eclipse, I'm getting lots of interest in astronomy. Maybe we should get little Doris or little Johnny a telescope. Yes, you should. It's an awesome gift. And yes, you should pick up a copy of Star Mentor, because that will make your gift of a new telescope complete. Thank you, everybody, for joining us. Be back with us next week, Monday, 4 o'clock, as always, on YouTube, Twitter, Twitch, and of course, Explore Scientific Live. We'll be back with you with another exciting program next week. And if you've got suggestions, gosh, I want to know about, send those in, email them, or send a smoke signal, whatever you need to do. And you know what? I'd love to take your suggestion and make a program or a segment out of it. So thanks, everybody. It's great to be back for a third season of How Do You Know? And we'll see you again next Monday.